Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside as we continue our Chapter 8 stuff on similarity for the Big Ideas Math Integrated Math 2 textbook on similar polygons. Now this will start to take more form than just dilations, and now just more into what it is about similarity that we do and how we test for it, and when it is there, how we find values, and stuff like that. A lot of things with proportions. Things will set up as fractions generally, but, we solve things along the way. So let's take a look at what this looks like and, look at the problem set. If you need to find anything, go to the description section down below and find the PDF of what I'm about to show you right here, as well as timestamps to any of the parts of what I do, because I begin with the lecture portion and then I go to the problem set of these for Big Ideas Math. So without further ado, let's go ahead and get started and see what we got. We're going to be using similarity statements to whatever that specifically means. I'm thinking mathematical similarity statements. I don't know how they're saying it. Find corresponding lengths in similar polygons. Now the word corresponding is something you're going to hear me say a lot, at least corresponding parts, corresponding sides, corresponding angles. Find perimeters and areas of similar polygons. Interesting. We actually hinted at this once, I think in section 8.1. It might have been 8.2, but I can't remember. And decide whether polygons are similar. So just that whole check in that test. And I don't know, this is on similar polygons as a whole, not just triangles. We're going to get deeper into just similar triangles, triangle similarity later. So I think there's going to be some amount of obviousness to it here, whereas there will be very specific tests with triangles later. All right, using similarity statements. Yes, this is more mathematical statements as opposed to like writing something as a statement. Corresponding parts of similar polygons. In the diagram below, triangle ABC is similar to triangle DEF. You see ABC, you see DEF. You can write triangle ABC is similar to triangle DEF as the thing with the squiggly line right here. So if you've seen the congruent symbol, and hopefully you have because I might make mention of it later, it's the equal sign with the squiggly above. This is just the squiggly line right here. It doesn't mean approximately equal to or anything. It means the word similar, and we've so far understood that the word similar means same angle measures, but different lengths that grow in some sort of way that you can make a dilation out of it. You can make a composition of transformations to get to where you want to be there. A similarity, transformation preserves angle measure, so corresponding angles are congruent. I should just read what they say. A similarity transformation also enlarges or reduces side lengths by a scale factor k, so corresponding side lengths are proportional. So angles are congruent, but sides are proportional. That's where similarity applies. So when they also say, and they're going to show right here the parts that correspond, when they say ABC similar to DEF, that means that A specifically corresponds with D, B with E, and C with F. And not just their angles, but AB with DE and things like that as well. And then you can see right here for parts that C multiplies with some scale factor K to become K times C, A multiplies with the scale factor K here, etc. So you can see the angles measures that correspond are congruent. And then when you do a division of side lengths, DE over AB, you're getting that same scale factor of K for all three sets of corresponding sides. This is a similarity ratio. Using similarity statements. So in the diagram, we have triangle RST similar to triangle XYZ. And it's going to be made obvious later, by the way, but they aren't always going to be facing the same direction like this, and your goal is to kind of make them face the same direction so you can find those corresponding parts more easily. Find the scale factor from RST to XYZ. List all pairs of congruent angles and write the ratios of the corresponding side lengths in a statement of proportionality. So let's go ahead and see how they write it so we can write it the exact same way later. First of all, we come up with the similarity ratio, or excuse me, the scale factor from RST to XYZ, what you got to multiply by to reduce, which would be a number less than 1. That means we got to divide these parts by their parts that correspond right here, like 15 over 35, you can see, or 25, you can see right there, 18 over 30, you see here, and 12 over 20. And it should all be 3/5, and you're seeing the test in all three sets. I don't know if I need to write all three when I do the problems, because the whole point is they are similar, so only one test alone should work, but you got to make sure you're also dividing corresponding parts. Here are the angles that are congruent. And by the way, just remember letter order matters. 1, 2, 3 with 1, 2, 3. Ones together. R with X. Boom. S with Y. Boom. T with Z. Boom. By the way, the reason I do the lecture stuff is not only to make sense of it for you and myself, it's to make sure that I don't have to say as much later. So I will say as much as I need to write speed-wise, but I use the lecture portion for this now. All of these, if I divide xy by rs, whoops, I got to fit these all in one shot. Xy by rs, I'm getting the same thing as if I divide yz, y's right here, yz by st, and then zx by tr right there. So those three sets are going to be the same division for the similarity ratio. There's another example that I will leave for when we do our own problems. I should probably move myself over here. Finding corresponding lengths in similar polygons. Okay, if we know that they're similar, then the ratios should always be equal to the scale factor of the similar polygons. Anytime that we do a division for these two polygons that are similar, find parts that correspond, use that similarity ratio, and apply it to end up finding a missing value. Such as if these are facing the same direction, DF is to MP and stuff like that, but I gotta find X. EF is to NP in that same way. And they're gonna write out a proportion here. And I could speak worlds on this. For one, there's more than one way to write these, as in which version of the fraction you want to write. But just make sure you have, the only two things that matter are make sure you have parts that correspond together and make sure that they flow in the same direction. And here's what I mean by that. Mn over dE. Here's Mn, here's dE. Mn over dE, notice how I draw the arrow, it's the flow and the directionality. They correspond, first of all. And here's the direction that I go. I can go that direction as long as NP is on this part and it goes with EF corresponding to it in the same direction. I got to go from this triangle to this triangle for both of them in that direction, and those parts got to correspond. Now, another version of this you can do is you could stay within the same triangle, go from here to here, Mn, and this is where I say I could talk laps around this. Mn can divide by Np, cool, as long as you go corresponding part to Mn here, divided by the other corresponding part, and it goes in that direction. You'll still get the same value when you solve. Anyway, here's a fraction, and like I said, you can work off these fractions pretty easily because you're just solving a variable. You cross multiply, although they could have reduced this fraction first. You cross multiply and divide by 18 and you get x is 25. That'll fill out that similarity ratio as everything else is reducing to that amount or enlarging. I don't know which way they're saying it. Another example of finding a corresponding length, you have two similar triangles, but in this case, never mind. In this case, this is similar to that. T corresponds with x. There's a reflection involved, but T corresponds with x. Find the length of the altitude PS right here. So they first start by finding the scale factor. How much does it go from this triangle to this triangle? They divide the 8s by 6s, or this entire length, I guess you should say. And they get 3/4. So it's a 3/4 scale factor. So if 20 is the value right here, 20 is the value that goes here as well. 3 is to 4 as this is to 20. You can then cross multiply and solve with that as well. So it's just a setup of proportionality. You could multiply 20 by 3/4. That's technically what they do. But setting it up as a proportion is probably the way to go always in those. Okay, some other examples down below. Just keep moving forward. Finding perimeters in areas of similar polygons. So the thing about perimeters is a form of length. Length is one-dimensional, like any other sets of lengths that we do with proportionality. So whatever the scale factor is, or the similarity ratio is of lengths, like this to this, let's say it's 1/2, the perimeter is going to maintain the same thing, because all you're doing is adding other lengths. So the perimeter of this would still be half of this one, for example. That stays identical. The ratio of the perimeters is equal to the ratios of their corresponding side lengths. I'll save the however for area. It doesn't seem like they're saying area yet. Here's an example. A town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. The new pool will be similar in shape to an Olympic pool, but will have a length of 40 meters. Find perimeters of an Olympic pool and the new pool. So without even doing, and I don't know how they're going to go about it, but there are two options here. Without finding the other length right here, you could find the perimeter of this original pool, which is probably their plan. Find the perimeter of this original pool, compare the 40 to the 50, and apply that to the new pool. So this pool's perimeter is going to be 50 plus 25 plus 50 plus 25. That's 150. And 40 compares to 50. 40 is 4/5 of 50. So we'd have to take 4/5 of 150, which I think is 120. So the other perimeter should be 120 meters, basically. So that's one version of the plan. It looks like they're doing exactly that. 150 meters for the perimeter of 1. Take 4/5 of that 150, or set it up as a proportion, and you get 120 meters for the other. And I guess that's how they did it. Alternatively, we could take 4/5 of 50, 4/5 of 25, and find the perimeter based on those numbers alone. But the whole point is, if you have the perimeter of 1, you can still apply it because it should share the same similarity ratio. I was going to say scale factor, but I don't think that really works there. Areas of similar polygons is different, though. Areas are not equal to the corresponding side ratio lengths. It is equal to the square of those ratios of corresponding side lengths. Now, I got to do this in a problem, in an exploration problem with you guys on another set, and I explained it then, but this is where it's actually taught. Here's what this means, and they have these things here once more, but if this was a 1-to-2 ratio here, you can't see that too, but if this was a 1-to-2 ratio here, where, every length was half of this length, I should put 1-to-2 on the thing, 1-to-2, this area would be 1 to then 4. You square 1. 1 squared is 1 and 2 squared is 4. The area would be 4 times as much. Now, again, I did it in another problem, and I used TVs as an example. If I had a 30-inch television and a 60-inch television, and they measure them by the diagonals, but it doesn't matter how they measure them. If it's a length, that's a very certain kind of measurement. 60 is twice as much as 30. So I can see where you make the argument that, well, it's twice as big of a TV. Well, if you think about what those televisions actually look like, if you imagine what those televisions look like, 30 inches and 60 inches, say this is the 30-inch one and this is the 60-inch one, it depends on how you're arguing measurements. My question is, how many of these 30-inch TVs can fit inside the 60-inch TV? 1, 2, 3, 4. Not just 2 of them, but 4 of them. Right? So there's a difference between one and the other when it comes to that. So it depends. Twice as long, sure. But it goes in 2 different dimensions. That's why you double up the doubling. So 2 squared is 4. So 4 times as many. Anyway, in the diagram here, here's an example. In the diagram, these 2 triangles are similar. Find the area of triangle DEF. If I know the area of triangle ABC is 36 square centimeters, and you have this length 10 and this length 5, and that means that this triangle's lengths are twice as big as this many. Does that mean that this triangle is twice as big as this triangle in area? No, it's actually 4 times bigger. This is exactly what we talked about with the televisions. You can fit 4 of these triangles inside this one. Okay, 4 of them could, like 1, 2, 3, 4. So it's 4 times as big. That means that the area of this one should be 4 times smaller than that one, right? So this is what they're going to work out. They're going to work out that 10-to-5 ratio of the side lengths. You could write it as 2. They decided to not divide and just square it straight up. And then they did cross multiply and solve. But then their area of the other one is 9 square centimeters. 9 is 4 times less than 36. Not half, it's not 18, but a quarter of it. A quarter of it. And that's what we do for similarity of those ones. And then we have other examples deciding whether polygons are similar. So we have this pentagon ABCDE and KLQRP. They say, decide whether they're similar and explain your reasoning. Well, one thing you could do is determine which parts are supposed to correspond. You can tell it looks like a reflection. A looks like it should correspond to K, and as you move throughout, it looks like, you can see what you can see. This 8 should be with the 12, and the 6 with the 9, and the 4 with the 6, etc. But we got to make sure that they all fall in correspondence of each other, for one thing. But is that still a guarantee? Let's see what they say. Corresponding sides of the pentagons are proportional with a scale factor of 2/3. Okay, so everything is 2 to 3, 2 to 3. However, this does not necessarily mean the pentagons are similar. A dilation with center A and scale factor 2/3 moves ABCDE into AFGHJ. Basically, they just made another one that looks like this. Then a reflection moves this thing over here. So they took this green guy and flipped it over and became the green guy over here. And they say it doesn't exactly coincide. Okay, so we're going based off the appearance of the drawing, which is fine. It's just we got to know to draw it exactly, to look exactly like the other. And look, I get it. This looks, well, they both look acute here. This looks like it angles downward. This looks like it angles upward, right? So when you flip it over, that angles upward, this angles downward. So no, they don't have matching parts unless there's a rotation to be had, but they created the problem, so clearly they know it's not going to be similar. But it looks like we still have to describe things with the transformations to work that out. All right, that doesn't look, the blue doesn't look similar to the red there, but it does look similar here. You got to do a rotation and dilation. That's other problems to do. Are we done yet with this stuff? Okay, we're finally, sorry. I was like, this is, it's bearing down on me a little bit with this lecture. That was a lot of pages. Okay, let's do the vocabulary and core concept check and take a look at what they want us to answer here. Then we'll do the official problem set. Complete the sentence. For two figures to be similar, the corresponding angles must be congruent. Must be. Absolutely. And the corresponding side lengths must be not congruent, but proportional. So similarity is not the same as congruence when it comes to polygons, when it comes to figures. So when figures are congruent, corresponding angles are congruent, corresponding sides are congruent. But here they're proportional. They have a certain scale factor that you can apply. And by the way, they keep saying the phrase scale factor. If I ever say the phrase, because I've already said it, if I ever say the phrase similarity ratio, that means the same thing. What you're multiplying by to keep the item similar from one thing to another. Different word, same question. Which is different? Find both answers. If I ask what is the scale factor, that'd be a question like A. What is the ratio of their areas? Remember, scale factor and area ratio are specifically two different things, so I know that one is different, but which one is different from here? What is the ratio of their corresponding side lengths? A, that is also the same as scale factor in this case. What is the ratio of perimeters? That still applies with the same thing as ratio of corresponding side lengths. Those are equal. That is A. The ratio of areas is the square of the ratio of the corresponding side lengths, not equal to. And there are two objects right here, and they're not asking us to answer the question, but that's it there. All right, guys, so that is both the lecture portion and the vocabulary and core concept check. We are now going to move forward to the official problem set. So let's get ready to go as I'm preparing myself as well with this number 3 coming up. So without further ado, guys, let's go ahead and get started, shall we? In exercises 3 and 4, we're going to find the scale factor. Then we're going to list all pairs of congruent angles and write the ratios of the corresponding side lengths in a statement of proportionality. Okay, so I'll leave the figures over there, and I'll go ahead and write some things over here. In finding the scale factor, we have to make sure we identify which parts correspond based on the appearance and, probably more importantly, based on the comparisons of side lengths. 4.5 is the smallest side length in this triangle. 6 is the smallest in this triangle. 6.75 is the biggest in this triangle. 9 is the biggest in this triangle. If there is similarity, then the smallest should correspond with smallest, biggest with biggest, etc. That'll probably make more sense when we get triangles that are flipped over and stuff. Anyway, we're going from, and it sounds like it's important to say which one you're going from and to. This is an enlargement, so the scale factor should be numbered more than 1. So we should be dividing, say, this number by this number. I'm going to be dividing 6 by 4.5. 6 over 4.5. They say they're similar, so we're going to say equals. It's not a question. It's equal to the same thing as 8 over 6, which is equal to the same thing as 9 over 6.75. Now, I don't know if they wanted I'm just going to reduce the fraction. This is 4/3. I'm really looking at the 8/6 to get me there, but this is going to be the scale factor. I'll put K equals for that part. Let me get a little water hit here as you look at that. Yeah, the decimal would be 1.3 repeating, but these are all the same. Here's a reduced fraction version of that with integers. List all pairs of congruent angles. Now I can do, oh, by the way, I didn't notice this. I don't know why. There's a similarity statement, so I should also know what corresponds with this right here. A and L are the first letter each, B and M are the second letter each, and C and N are the third letter each. And this is good for me to do the congruent angles. Angle A is congruent with angle L. Angle B is congruent with angle M. And honestly, I'm not even looking at the figure. I am looking at the statement. Angle C is congruent with angle N. So there are those three. And then write all the corresponding side lengths in the statement of proportionality, very similar to what we just did here. So we can say that the length of, like literally, the 6 and the 4.5 and stuff, the length of LN divided by the length of AC is equal to the length of ML. Oh, let me do that one last. I hate when it does that. is equal to the length of MN over the length of BC. And that's equal to the length of LN over the length of AC. So all of these fall in proportionality. And you know what? It's really good if you write these things. Keep in mind you would only technically need two ratios to compare. But this is good because we have to do proportionality later. So what we're writing applies later. And I looked at the figure for it, but I didn't need to because I can also look at letters that specifically correspond there. That's number 3. Let's go to number 4. These are two quadrilaterals, DEFG and PQRS. And this is one of those things where I said if you take a look, you can probably tell which parts are supposed to correspond. If you look at side lengths, you can tell which parts are supposed to correspond. But you can also look at the statement. D corresponds with P. Well, D is right here, and P is right here, clearly in different spots. This item, and let me kind of show you, this item is clearly a rotation of what it could be. Obviously, it's made much bigger if I do that. But if I took this thing and did this to it, I know it'll be upside down. But if I did this to it, take a look at now how they go the same direction. This might, even though it's upside down, it might be helpful to see it this way to see which parts specifically correspond. I always recommend that you redraw your items, not upside down, but you redraw your items so they face the same direction so you can correspond parts. And now they actually do. And again, I acknowledge they're upside down. But let's go ahead and find the reduction similarity ratio, or scale factor rather. K is going to be, we have 1 to 3, and 2 to 6, and 3 to 9, and 4 to 12. I'm ranking up the sizes like that, which is the same as 1/3, which we already had as that answer. And I don't know if they needed us to do all of that, but all of those are the same sets there. Now, as far as angles that are congruent, once again, you can either look at the statement or look at the way that I redrew this, if you will. Angle D is congruent to angle P. Angle E is congruent to angle Q. I'm actually looking at the diagram this time for it. Angle F is congruent to angle R. And angle G is congruent to angle S, which the S, upside down, is still an S. And mine looks like a 5. Okay. Now the third set is to write out these the proportionality of these statements like I did above here. So I can do I'll start with PQ. PQ is to DE as QR is to EF as RS is to FG as PS is to DG. There we go. Okay, that is it for 3 and 4. By the way, how many problems do we have? 56. Okay, well, we've done 2. And 23 minutes in. Okay. In exercises 5 through 8, the polygons are similar. Find the value of x. So, and once again, unless there's something I need to redraw, and I'll probably just do what I did for the last one. I can kind of reconfigure it, and even if I have to flip something over and make it backwards or upside down, just go with it if it's drawn a different direction. We'll play with it. They tell you they're similar. Now, here's a difference. They didn't write the similarity statement, so we got to go by, once again, both side lengths and look at where the angles are that correspond that should be congruent. If the triangles are similar, the corresponding angles will be congruent. So they're facing the same direction. We all good. So we got to find out x, right? X is one of the missing lengths. X corresponds with 20. I can start by writing out, it doesn't matter whether we talk about enlargement or reduction, x over 20, 20 over x, one or the other, as long as when I do the next statement, I go big to small. I go this direction. I can do 18 over 12. I could do 21 over 14. I'm going to do 18 over 12 because I just drew an arrow there. So x is to 20 as 18 is to 12. Now I can look to cross multiply and solve. Little word to the wise, if you want to make this a little bit easier for yourself, reduce fractions wherever you can. 18 and 12 can both divide by 6 and you get 3 over 2. Heck, I could technically reduce the 20 and 2. They're not a fraction, but I can make everything twice as small on the bottom. I won't. I'll go ahead and cross multiply now. 2x equals 60, so x equals 30. There's a lot of wasted space for that problem. I should have gone to the right. But that is the answer to that one. And I'm not saying to double check anything right there, but it should be more than 20 at the very least. It should be 1.5 times more than 20. Okay, number 6. So these two triangles look like, and this is, I'm probably not going to do this each time. I just want to show on this one. This looks like a reflection. So if I take this thing, I kind of copied pasted it there. If I took this thing and flipped it over, literally like flip like that. Again, I'm making it backwards from what it was. But if I flip this thing over, ooh, something happened to my, no. Okay. You can see now our parts should truly correspond right here. This should correspond with that, things like that. So X is with the HJ. I think that's a J. So let's go ahead and get that one sorted out. Let's say we put X on the bottom this time. So this 18, yes, it's an 18. 18 is to X as 12 is to 16. You know, maybe I shouldn't flip that thing over. That's hard to read. 18 is to X as 12 is to 16. Word to the wise never hurt. Reduce that fraction once more to 3/4. 18 over X equals 3/4. Easier for me to multiply. I still don't know 4 times 18. 72. 72 equals 3x. Divide by 3 and you get X equals 24. So we're just finding the missing value, or the value of X in all these situations, and it's based on what I'm doing there, as you see. Number 7. Where's X? There it is. These are facing the same direction, so it seems... now, I said I could do this as well, so let me do it on this problem here. X is to 13 as 22 is to 26. As long as parts correspond, you can write... There's more than one way to write this, guys. As long as you write something that corresponds and it goes from one part to another and then the same corresponding parts and stuff, this can all work out. They probably don't want you to do this way because we never found a similarity ratio. 22 over 26 is not a similarity ratio here, guys. It's just a ratio that can be used in a proportionality test. Now, once again, I can reduce that fraction, but it doesn't mean it won't work. Oh, look at that. You know what X is good without cross multiplying and solving? I don't know, 13 times 11. I can figure it out, 143. But X over 13 is 11 over 13. What is X? 11. Now, literally, I could just say multiply both sides by 13 and I'm good. But reducing the fraction paid its dividends there on that one. So it looks like, oh, I mean, this was also clear as day. I probably should have just gone with it. 26 is twice as big as 13, and that's how we work it. All right, and number 8, and then I got to clear my hiccups here. Plus this thing, you can notice the pen tool isn't showing up, so I want to probably fix that as well. Number 8, facing the same direction once again. This X is to 8. As, 15 is to 10. Why not? So let's go number 8. X is to 8 as 15 is to 10. And hopefully you know what I'm saying when I'm saying this is to this as this is to that. Let me reduce the fraction first. One of my common ones that I tend to say just because it's one that I remember most. In fact, I'm going to multiply both sides by 8 right here. 3 times 8 over 2. 24 over 2 is 12. X is 12. Is something like a pebble is to a boulder as a baby is to a blank. And then we're answering that question with, like, if I give you a multiple choice option, you know, whatever. A pebble is a small version of a rock. A boulder is a big version of a rock. A baby is a small version of a human. A what is a big version of a human, right? Like a man, you know, an adult. Something like that. So that's the kind of thing of when I say those analogous things, that's the same thing when it comes to proportionality, and that's what we think about. Let me pause this for one moment while I clear my hiccups and such. All right. We finished 8, right? Let me see. Yeah, okay. Okay, in exercises 9 and 10, the black triangles are similar. Identify the type of segment shown in blue and find the value of the variable. Okay, the type of segment is called an altitude. But let's go over... Here's what I really like about this problem is they say things are similar, but they really hide away which parts are supposed to represent what, unless you really know what you're looking at. Like, it looks like this is a rotation and a dilation and things like that. But these two parts don't correspond here. And the reason I know that is because of how they're representing things. When you have parallel lines here, that means you have congruent alternate interior angles. Like that. Those are congruent. These are congruent here. And if you want to know a third set that's congruent, we got, whoopsie, let's do two like that. We got vertical angles right here. So these two are congruent here. So if you notice, this thing needs to take itself and flip itself over that way to these to be congruent in that way. So 18 doesn't correspond with here. 18 corresponds with 27. Anyway, I just want to bring that up because that's going to be how we build a similarity ratio of this thing. Number 9, 18 goes to 27 here. Now, these are not lengths of sides, but they correspond because they are altitudes from this set of congruent angles to this set of corresponding sides. So the 16 would correspond with the x in the exact same way. And once again, they are called altitudes. They did ask you to identify the type of segment in blue, and that's what this one is. So it goes like that, and I'm going to, again, the book didn't really do much on reducing fractions. I'm going to keep doing that for my sake of, I don't know, 27 times 16, and this will still get me the same answer. 3 times 16 is 48, was a 2x, and then x is 24, so that's the length of that. And, you know, once again, we're doing similarity ratio stuff, so 18 is 2/3 of 27, 16 is 2/3 of what number, right? That's 24, and that's what we're getting. Okay, number 10. We have another set. These aren't altitudes anymore. If you know, altitudes are all about perpendicular to a side from a vertex and such. But what we have here, okay, we have medians. Oh, let me write out altitudes for the first part. But because congruent parts, those mean that this is a midpoint. And a midpoint from a vertex, those are known as medians. We did that in chapter 6. Anyway, these are altitudes. Let me put that. Altitudes. Altitudes. Anyway, this one here actually is not a rotation unlike the last one. This one's more like a reflection because you can see the parts that correspond that are congruent here by the single arc marks, and then the other one has double arc marks there. So this time, y corresponds with 18. Well, I mean, those are the only parts that are marked. So y corresponds with 18 as y minus 1 on that same small triangle corresponds with 16, and y minus 1 and 16 are once again medians. I'll do it in blue. Medians. Does that change what the answer is going to be? No, but it helps that they both are corresponding to each other. They're representing the same kind of length in these triangles. If we cross multiply here, we'll get 16y equals. Now, 18 multiplies by all of y minus 1. I want to make sure that you understand that. It's not just times y. It's a distribution, if you will. So 18y minus 18. I can subtract 16y from both sides, add 18 to both sides, divide both sides by 2, and I get y equals 9. Do I just solve for the variable? Yes. Find the value of the variable. So that's number 10. All right, numbers 11 and 12. RSTU is similar to ABCD, letter order matters for parts that correspond. Find the ratio of their perimeters. The ratio of their perimeters will be equal to the similarity ratio, just so you're aware. The only thing is I don't know which direction they want you to do them, if it needs to specifically go from this to that or something. It seems like that's kind of what they've been doing each time, so I'll keep that. So I'm just going to put R sub P. I think I used to do that at the time. But the ratio of perimeters is the same thing as their similarity ratio K. It's, R, S, T, U, A, B, C, D, right? So 12 corresponds with 8, not with 14, but with 8. So I'm going to do 8 over 12, which is 2/3. So the ratio of the perimeters is 2/3. I don't need to find the other lengths. I don't even need to find the ratios, the perimeters. I just need to find the similarity ratio for these things, and that's what it will work out to. Now, I explained that more in the lecture portion, by the way, but that's going to work out like that for perimeters, not for area, but for perimeters. Number 12, same thing, RSTU for ABCD. From RS to AB, it looks like an enlargement here, so I'm going to divide 24 by 18, but it's the same thing. The ratio of perimeters is the same as the scale factor, which is 24 over 18, which is 4/3. And look, this one looks more like a rectangle. I can't guarantee it is, but this is not a rectangle. They're not expecting you to find the perimeters. They just want to say compare the perimeters. How much bigger, how many times bigger is one versus the other. In exercises 13 to 16, two polygons are similar. The perimeter of one polygon and the ratio of the corresponding side lengths are given. Find the perimeter of the other polygon. So on number 13, you have perimeter of small polygon. Sorry, I feel like I have to write this. Or smaller polygon equals 48 centimeters, and ratio is 2 to 3. So this is where directionality matters in what you do. When it comes to writing a proportion, we're going to find the perimeter of the larger, smaller. Find the perimeter of the larger polygon with this. Next time I'll put P small. So because here I'm going to do this. The perimeter of the smaller one is 48. The perimeter of the larger one, we don't know. P larger. This will be equal to the same thing as the ratio of the corresponding sides of this thing, because they're all sets of lengths. It's 2 to 3, but the direction of this matters. I put 48 on top, the perimeter smaller over perimeter larger, because this is smaller and this is larger, and that's how they compare. So when I solve for this P here, I'll cross multiply. 2 times, I'm just going to put P. 2 times P is 3 times 48, 144. Divide by 2, and you get P of the larger one. Maybe I'll put P sub L. This is just, it's too much writing. 72 centimeters. So the perimeter of the larger one is 72 centimeters there. I don't know any of the side lengths. I don't even know what kind of polygon it is, but I know that that's how they compare. Number 14. The perimeter of the smaller one is 66 feet, and the ratio is 3 to 4. So P sub S, now I'm figuring it out, is 66 feet. Ratio is 3 to 4. So once again, same kind of setup. 66 feet is to the perimeter of the larger one, as 3 is to 4. That is an L. That is a cursive L. Apologies on that. Cross multiply. 3 times P sub L is 4 times 66, 264. Divide by 3, P sub L equals, I don't know, 88? Oh, I should have known that from this. 88 feet. So the perimeter of the larger one is 88 feet. Number 15. Now we have the perimeter of the larger polygon. So this is a P sub L, if you will. P sub L equals 120 yards. And the ratio is 1 to 6. Now, for being 1 to 6, that is from smaller to larger. So when I do this one, I have the larger one. I need to find the perimeter of the smaller one. I'm going to put that on top. And I don't need to put it on top. Whoops. I don't need to put it on top, but I'm going to compare it to the 1 to 6 here. So perimeter of the smaller over 120 yards is going to be equal to that 1 to 6, because this is small over large, small over large. So order matters here. Cross multiply 6 times perimeter of small, and you don't have to cross multiply, but that's how I'm going to work it out. 120, and then divide by 6 again where it was already, and you get 20. P sub S is 20 yards. Perimeter of the smaller one is 20 yards. Number 16 is the same but different numbers. Okay, so perimeter of larger is 85 meters. Ratio is 2 to 5. So, I mean, literally, here's what I can do. The smaller one is 2/5 that of 85. So I can figure that out too. I think it's going to be 34. But perimeter of smaller over 85 meters equals 2 to 5. Again, okay, I shouldn't really cross multiply. I should multiply both sides by 85. This is where I should really listen to the book. Multiply both sides by 85. And perimeter of the smaller is going to be 85 over 5 is 17. And 2 times 17 is 34. I think that's what I said before. 34 meters. Okay, that's those ones. Let's move forward. Number 17. A school gymnasium is being remodeled. The basketball court will be similar to an NCAA basketball court, which has a length of 94 feet and a width of 50 feet. It says similar. Like, similar, proportionally. The school plans to make the width of the new court 45 feet. Find the perimeters of an NCAA court and of the new court in the school. So if I draw out my rectangular NCAA court here, I have one that is 94 feet by 50 feet. The perimeter of this guy, it's rectangular, so you're going to have two 94s plus two 50s. Well, that's 100, and that's 188, excuse me. So 288 feet. Okay, that's the perimeter of the NCAA court. So I'll write that, NCAA. Now this other one here, we know a little bit smaller. Instead of a 50-foot width, we have a 45-foot width, 45 feet. Now you have a couple options on how you can find the perimeter, but let's do it in the same way that we kind of used before. Let's set up a proportion for this thing to find its perimeter of the school gymnasium. 50 and 45 correspond. We can come up with the similarity ratio as far as a reduction here. Whatever 45 over 50 is, when you compare those two, this to this, is going to be the same thing as the perimeter of this school court over 288. So if I multiply both sides by 288, I'm taking, and by the way, 45 50ths is 9/10. I got to take 9/10. So this is 9/10. I got to take 9/10 of 288. I mean, that's what's happening there. I don't know what that answer is. I got to, it's a decimal, unless I did something wrong in this other thing here. I'm trying to do it in my head. Sorry. 260. Oh gosh. 259.2. 259.2 feet, which then must mean, and I got to make sure that's right, but which must mean that it probably is, that this one would have been a decimal here as well. So I'm going to guess 259.2 feet for that perimeter and this perimeter as well. Did they want something else? Find the perimeters of those two courts. No, that's it. So that's what I'm going with on that one. But yeah, it should be I don't know if I calculated it correctly, but it should be a decimal, I guess, when all said and done on that one. Okay. And by the way, units have mattered almost this entire time. I hope that you've been following along with that. No naked numbers when they give you units. I just spilled all over. Number 18, modeling with mathematics. Your family has decided to put a rectangular patio in your backyard similar to the shape of your backyard. Your backyard has a length of 45 feet and a width of 20 feet. The length of your new patio is 18 feet. Find the perimeters of your backyard and of the patio. Decided to put a rectangular patio in the backyard. Oh, okay, so it's in the backyard. I totally misread the thing. I thought they said your family, like your parents have decided to copy you and make their own patio like yours. Okay, so you have a backyard that's like this. Okay, it's 45 feet in length and 20 feet in width. Now, the patio, maybe, I don't know, let's say the patio's like right there, right? The thing is, though, you have to be very careful with what they say here. You see the 18, and you might think that the 18 is supposed to be like this and correspond with the 20. No, they said the word length. So it's all about parts that correspond. This is 18. This corresponds with the 45. So our unknown, which, by the way, we don't really need to know, but our unknown would be x in this case here. We need to do the same thing that we did before, find the perimeters of your backyard and the patio. So I'll put perimeter of backyard, P sub B, PB, is two 45s and two 20s. Hopefully you know how that works for rectangles to do that. 90 plus 40 is 130 feet. And now perimeter of the patio, PP, is going to be, actually before I just write equals, let's do that similarity ratio thing. It's going to be a reduction, and we got to divide 18 by 45 because the perimeter of our patio will be that equivalence of 130 feet, the perimeter of the entire backyard. So we could do the cross multiply and solve, but of course another reduction here. Divide these by 9. You get 2/5. So we're going to take 2/5 of 130, right? That's basically what's going on here. So P sub P equals, I don't know 2/5 of 130 is because I don't know what 130 divided by 5 is. 130 divided by 5 is 26. So times 2 is 52. So 2/5 of 130, which is 52 feet. That's the perimeter of the entire patio there. And that's what we got, at least if I trust my own math, and I feel like I should. Let's go with it. So 130 for the other one. Did I put that? Yes. Okay. All right. Hold on. I just lost my... Where's my little workstation? There it is. Okay. Let's go to number 19. Numbers 19 to 22. The polygons are similar. The area of one polygon is given. Find the area of the other polygon. So now we're not talking about perimeters. We're talking about areas. Perimeter ratios are equal to scale factors and ratios of corresponding sides. Area ratios are the square of these things here. So area ratio equals whatever ratio we want to do squared. This thing has an area of 27 square feet. It's not your goal to figure out that this is like 9 or something. Your goal is to just compare this. 6 is twice as big as 3. Doesn't mean the area is twice as big. 6 is twice as big as 3, but we got to square that result. We got to square 2. And I know that the book does more like 6 squared and 3 squared. We got to square 2 when we get 4. This is the area ratio. This does not mean this is the answer. The area of this thing isn't 4. The area ratio, to enlarge it, the area is 4 times bigger than the other one. So 27 over the area that I'm trying to find is equal, actually I should say area. The area over that I'm trying to find over 27 square feet is equal to 4 to 1. 4 to 1. 4 times as big. You square those areas. Check out once again, the lecture portion and hear more of what I had to say there if it kind of helps. And that's 108 square feet. And once again, the whole idea of the 4 instead of 2. Wait, why is it 4 times bigger? Because you can fit 4 of these inside of here, right? 4 of those can fit inside. That's what we're doing. Okay, number 20. The area of the smaller one is 10 square centimeters of the triangle. And it doesn't matter what kind of polygon this is. They give you an area, so we're just comparing from there. So the area ratio is going to be 12 to 4 as an enlargement, squared, which is 3 squared, which is 9. Now, the 3, guys, by the way, is the similarity ratio, the scale factor. We're squaring it. So when I get the area and divide it by 10 square centimeters, the area of the smaller one, it'll be the same as doing 9 divided by 1. I could just put 9, by the way. Multiply the 10 out, and you get 90. So 90 square centimeters for this big triangle. Without knowing the height, without knowing yada yada. Number 21. Whew, big in comparison. However, we're going to find the smaller one, right? So on number 21, it doesn't matter if we write it as an enlargement, reduction, whatever, but the area ratio here, it looks like they all kind of call them enlargements. So let's just do the same thing. Let's do 20 over 4 squared, 5 squared, which is 25. This other rectangle is 25 times smaller than that guy here. But if I want to find the area of the smaller guy, let's say if I'm dividing 100 square inches divided by the area of the smaller guy, that's going to be the same thing as 25 to 1 in that case there. Cross multiply 25a equals 100. Divide by 25. The area here is 4 square inches. 4 inches of this and 4 square inches in total in area. And then lastly, number 22. Let's find the area of the smaller guy here. Let's kind of go the other direction this time. Let's try area ratio as 3 to 12. We'll take 3 because maybe you almost want to see a fraction in this way. You see 25, you're like, I got to put over 1? No, but seeing it as a proportion helps. 1/4 squared is 1 over 16. So this smaller triangle is 1/16 the area of that other guy. That's the way of saying that when I divide the area of the smaller guy by 96 square centimeters, the area of the bigger one, that's going to be the same as that 1 to 16th ratio. Let's keep the 16 over there. So 96 over 16, which is 6 square centimeters for the area of the smaller guy. And that's number 22. Okay, error analysis. Describe the error in finding the perimeter of triangle. Describe and correct the error in finding the perimeter of triangle B. The triangles are similar. So we have this guy. I'm figuring they're probably not getting corresponding parts right. The perimeter. 5 over 10. 5 over 10 equals 28 over x. Okay, 28 seems to probably represent the perimeter of this guy right here. 10 plus 6 plus 12 is 28. So the problem is they went from triangle A to triangle B here, even though here they went from B to A. The directionality was wrong when it comes to proportionality. This would say a pebble is to a boulder as a man is to a baby. They kind of went the wrong direction when it came to writing out their correspondence. So they did apply corresponding parts, but wrote the ratios in opposite directions. They also even found the correct perimeter. The perimeter is 28 of that thing. So let's fix that. We can still say 5 over 10. That's fine. 5 over 10 equals, but don't do 28 over x. By the way, x means the perimeter of triangle B. Put x over 28. This is triangle B is to triangle A, is triangle B is to triangle A. But this is the length of a side and its corresponding part, the length of perimeter, and the length of this perimeter. 5/10 is 1/2. And if I multiply by 28 and divide that by 2, I get 14. So x is 14. There are no units, but just units. Perimeter of triangle B. Okay. All right, there's the correction. Number 24. Describe and correct the error in finding the area. I'm going to guess they're not going to square values. Of rectangle B, the rectangles are similar. Area is 24 square units, and we have a side length of 6 and 18. And yep, they just wrote 6 over 18 equals 24 over x. This time they corresponded parts correctly. They went the proper direction for both, but area ratio is not the same as similarity ratio and perimeter ratio. You have to square your thing. The ratios of areas are the square of the scale factors, or of the scale factor. So they never squared their values. They never squared the ratio. Squared. All right. ... So let's go ahead and fix that. 6 over 18 is 24 over x is not quite there. We have to square 6 over 18. I got a text from message from one of my softball players. I gotta kind of respond to that. I'm gonna pause after this. So 24 over x, 6 over 18, and another thing, it's not an error, but they never reduced. I'm gonna reduce that. That's 1/3 squared. And 1/3 squared is 1/9. Actually, you know what? It's in a group chat with all of my other players. I think that they're gonna respond to each other that way. Cross multiply x, 9 times 24, 216. 216 square units for the bigger area, not just 72. You're really shorting it by saying that. That's another error. They never put square units like they did for the first guy. Okay, let's move forward. Number 25 and 26. Decide whether the red and blue polygons are similar. So I don't know what they want me to write, because here's the thing. We clearly have to go by the drawing a little bit. What I'm seeing in the drawing is probably a no. Just kind of like by angle measures. You can see these kind of look like 45-degree angle things here. Like here and right here or whatever. I guess 135-degree angles. And that one doesn't look like it to be that here. But if you compare things right here, if I did 22.5 compared to the 30, from blue to red and all that, that looks like the same thing as 30 over 40. Now, when I said 22.5 to 30, I said these parts probably correspond, and these parts probably correspond right here. And then we go blue to red, blue to red. Those are equal because they both equal 3/4. They actually do. So does 22.5 over 30. So that one's check. However, I'm going to type this. However, after careful consideration, after you do a a reflection, a dilation, all that kind of stuff. However, upon dilating the blue object, here, I'll say the red object, I'm going to reduce it, the red objects to 3/4 their lengths, the angle measures don't measures don't line up. The angles don't line up properly. Therefore, the polygons are not similar. Now, I'm not actually mapping that out, right? Because you have to draw it perfectly and stuff. But basically, one wouldn't look exactly like the other. It would kind of have more of like it would go more this way, up and out, and, you know, like that. Instead of not drawing it, and then I am drawing it. But, you know, it would just look like that instead. Even if it had the same lengths, not quite the same angles. Number 26. Well, here's the thing on 26. You don't have any parts that correspond when it comes to number comparisons. These 3s don't correspond to these 3s. They're congruent, but they're not corresponding parts. This 3, in all likelihood, corresponds with this little guy right here. Because what I see in this right angle symbol and the open gap and stuff is I need to take this blue, I need to rotate it a little bit, and then I need to dilate it upward, and boom, it goes that way. But that 3 seems to go to this guy right here, right? Now, although I don't have numbers that compare, I have the concepts that compare, which these are all congruent. And likewise in the similar, the possibly similar object, these are all congruent as well. And then these 3s, I don't know, there's nothing else that shows me. Oh, well, you know what this tells me? It tells me that these are, although not full quadrilaterals, these are essentially squares that are missing a 4th side. Squares that are missing their 4th side, because perpendicular diagonals with perpendicular bisected congruent diagonals are representative of parallelograms, rhombuses, and rectangles, and all things that squares would be. All squares are similar. I can say it that way. There are a lot of things that you can do there. The diagonals in each polygon, are correspondingly congruent to each other. What I mean by that is their respective parts, whatever. And there is enough information in each diagram to conclude that they are squares, which are that are missing a 4th side. In that case, all squares are similar. Therefore, these polygons are similar, especially since they're both missing one side. If one had one of those sides, well, then they're not similar anymore. They'd have different things. Okay, number 27, reasoning. Triangles ABC and DEF are similar. Which statement is correct? Select all that apply. So on number 27, I'm going to write this out, ABC and DEF. I'm not going to write out all the things, though. ABC is similar to triangle DEF. The thing that matters here is letter order. I don't even need to draw these, but if I did, I would draw it based on letter order. 1, 2, 3, 1, 2, 3. Let's find parts that correspond from these sets here. I'll copy and paste these over, and then I'm going to write numbers down and see if the parts correspond as long as the letters are what we see them to be here. So, what am I saying? What I'm saying is this. BC are letters 2 and 3. EF are letters 2 and 3. Those are corresponding parts. AC are letters 1 and 3. DF are letters 1 and 3. And this was ABC to DEF, ABC to DEF, ABC to DEF. So everything corresponds there. Everything works out. That's good. It's also about flow from one triangle to another. AB is to DE. That's 1, 2, and 1, 2. CA 3, 1 is to FE 3, 2. Uh-oh, those don't correspond there. No good. That is not one of the answers because the letter order, those are not corresponding parts. AB is to EF. EF is 2, 3. This is already a red flag, but let's take a look and make sure that nothing else is working. As 2, 3 is to 1, 2. Yeah, just because you're like, well, Mr. Robinson, they have the same numbers, 1, 2, and 1, 2, 2, 3, and 2, 3. They didn't write them in the proper corresponding parts. That also doesn't work that way. They need to make sure that they do AB to DE, BC to EF. And lastly, CA, 3, 1, is to FD, 3, 1, as BC, 2, 3, is to EF, 2, 3. From this triangle to this triangle, etc., that seems to also work out. That seems to be fine. So letters A and D seem to be the ones that are good there. There are a lot of other ways they could have tricked you. They could have said CB instead of BC. 2, 3, and 3, 2 are both the same thing when it comes to that thing. It's still the same segment. So they could have done that. They could have stayed within one triangle. How about this one? AB over CA is to DE over FD. Does that work? This is 1, 2 is to 3, 1, as 1, 2 is to 3, 1. And these are both in their own respective triangles. So this also would work. Probably not the way that they want to write it because they want to do corresponding parts, but you can be within there. You can flip the order, things like that. It should still be fine. Okay, an exercise. Oh, wait, is that the only problem? Yes. Numbers 28 to 34. In exercises 28 to 34, JKLM is similar to EFGH. Once again, one of those instances where they're not rotated the same way. So maybe it's best that I do that. And it does simply take a rotation. It's a 90-degree rotation that we're coming up with here. So let me kind of make that happen. I know things will be rotated letter number-wise, but it's easier than if they're flipped over, as far as I could tell. When they were flipped out, when they were reflected, that was kind of a pain. Okay, maybe I can hide a little bit of that last part there. Okay, so let's start with number 28 and answer whatever they want us to answer. But look how things correspond now. E with J, H with M, etc. And even the side lengths. Find the scale factor of JKLM to EFGH. So that is a reduction from JKLM to EFGH. Let's take the 8 and divide it with the 20. Those are the two only parts that correspond for which we know their actual side lengths. 8 over 20, which reduces to 2/5. This is the similarity ratio. This is the reduction from JKLM to EFGH. That is number 28. Number 29, find the scale factor of EFGH to JKLM. That should just be the opposite. So this K scale factor is 5 to 2. It's an enlargement, and it's literally just the opposite effect, 20 over 8. Number 30, find the values of X, Y, and Z. So each of these, we can use either scale factor, 2 to 5 or 5 to 2, reduction, enlargement, depends. Let's start with X. X from this KL corresponds with the 11. X goes to the 11. As, notice that's the enlargement. Well, X over 11. X is bigger than 11. As 5 is bigger than 2. We maintain that similarity ratio. And let's just go this way because I'm going to do a few of these. 2X equals 55. And therefore, X equals 55 over 2. I'm sure they probably want the decimal here. 27.5. I think that's the answer. That's not it for 30. We still need Y and Z. Now let's go Y is to 30. Y is to 30. Notice how I went from small, big. So let's go small, big. 2 is to 5. Just multiply both sides by 30. I should have done that with the X. So we get Y is 60 over 5, which is 12. 12 units in length. That's 2/5 of 30. And then 31. Let's be different. I have Z. Oh, Z is the angle measure. And whoops, it's not number 31, by the way. Corresponding angles are still congruent. Z is 65. And not even degrees. I have a symbol on the Z there. Number 31, find the perimeter of each polygon. Okay, it's probably best at this point that for the X value that I found, etc., that I just go ahead and replace it with what those values are. I think it's 27.5 there. So 27.5 on X, 12 on Y. Now, I don't know the length of ML. I could find it with a proportion, but since this already has a decimal, and since I already have all of the lengths on this one, I might as well find the perimeter of the small guy, apply the similarity ratio with the third one, and then we'll be good. This is perimeter of segment E, F, G, H. We're going to just add 12, 3, 11, and 8. and you get 15 plus 19, which is 34. 34 units. So the perimeter of JKLM, if I divided that by 34, that's big over small. That should be the same as, not 2, 5, big over 2, small. Like that. And I can multiply both sides by 34. Again, something the book would probably do there, especially since there's nothing to reduce. So 34 times 5 halves is 34 times 17. 5 times 17, which is 85 units. So that's perimeter of the small, perimeter of the big. And I think that's all of number 31 that we do need. That was 31, right? Okay. Let's go to 32. Find the ratio of the perimeters of JKLM to EFGH. That will be the exact same answer as number 28, because perimeter of ratios, or ratio of perimeters, is the same thing as your scale factor, which is 2/5. Wait, yes, the reduction, 2/5. Number 33, find the area of each polygon. So I'm trying to look at the things. These are both trapezoids. And the area of a trapezoid, you average your base and multiply by the height. The height is the difference, the distance between your two parallel parts here. So I'm going to do the area of EFGH. That's 1/2 the lengths of your bases, 3 and 8, and multiply that by 11. 1/2, average the bases, multiply by 11. So that's half of 11 times 11. Well, better for me to do half of 121, which is 60.5 square units. That's the area of EFGH. Now the area of, before I do that, oh, they say ratio of areas later. Okay, I'm not going to do that then. Let's write out that JKLM is that 5/2 similarity ratio, but we have to square it to equal the area of JKLM when I divide it by 60.5. Now 5/2 I can't actually square, so I'm going to, or reduce I should say, so I'm just going to go ahead and square it now. And this cross multiplication actually might require me to get a calculator here. Get a phone. I still have that message I might have to respond to. No one else did. Yeah, folks, just go to your calculators on this one. I'm going to be fine. 60.5 times 25/4. 3781.25. Did I write that right? No, I did not. 60.5 divided or times 25/4. 378.125. So area of JKLM. I hope those are the right numbers because they look kind of weird. 378.125 square units. Now, the reason why I did not do anything else is because I don't know the length of ML. Again, I could find it, but I'm just going to jump straight into it that way. And that will be that one. And then on the next problem, hold on, I just lost something here. And then on the next problem, we are writing out the area. I feel like this question is supposed to be asked beforehand, but we're finding the area ratio of JKLM to EFGH. Oh, that becomes reduced though. So on 34, I'm doing the area ratio from one to the other. I'm going to be squaring 2/5 because it's a reduction, and that's 4/25. But again, I feel like I kind of did more on this one to do within that problem. Okay, number 35, using structure. Rectangle A is similar to rectangle B. Rectangle A is side lengths of 6 and 12. Rectangle B is a side length of 18. What are the possible values for the length of the other side of rectangle B? Select all that apply. Got it. Okay, I was going to say, what are you talking about? Okay, so here's the thing. They call everything here a length. They just call them side lengths. So I have rectangle A. rectangle A looks like this. It's got 6 and 12. I don't know if they say feet or what. Now, rectangle B has kind of two options here. Whoops, not the same size, but rectangle B has a side length of 18. So you can either have rectangle B, if it was actually similar-esque, that if this, like either this could be 18 and this is the unknown, or 18 could be this, yikes, 18 could be the even bigger one right here, just make it supermassive. This could be the 18 here, and I don't know why I'm just making it supermassive there, and this could be the unknown. Actually, I think it wouldn't be, let me backtrack that. I think it'll actually be smaller. But this would be the 18 in this case, whereas the other one would be the unknown. So B or B, where this is the 18 and this is the unknown. It just depends on what you're corresponding. So we'll either correspond 6 with 18 and this 12 to this unknown, or we'll correspond 6 with the unknown and 12 with the 18. Because we don't know which side length part it's supposed to be. So we have options there. So let's use the blue option. 6 is to 18 as 12 is to x. And then the green option would be 6 is to x as 12 is to 18. So if I reduce this one here, I get 1/3 equals 12 over x, and x equals 36 is one option, because 12 is twice as much as 6, 36 is twice as much as 18. That's one way you can put it. And then if I reduce this guy, 6 over x equals 2/3, multiply both sides, cross multiply I should say, and divide, and I get x is 9. So this would be 9 on this case here, 9 to 18. 18 is twice as much as 9. It still works out. All right, that's number 30. Oh, hold on. That didn't really answer. So 36 and 9, it's going to be B and D, not C, not A. Number 36. How far are we going? 56. In table tennis, a table is a rectangle 9 feet long and 5 feet wide. 9 feet and 5 feet. A tennis court is, oh, that's not the ping pong. I just noticed the ping pong table is this little guy right there. That's okay. A tennis court is a rectangle 70, oh, maybe I should write them, 78 feet long and 36 feet wide. So 9 feet, 5 feet. And then this one is 78 feet and 36 feet. Are the two surfaces similar? Explain. If so, find the scale factor of the tennis court to the table. Now, I'll say, I don't know if these numbers are supposed to be accurate with respect to what they actually are, but if they are similar, I never knew that, and I have no way of I've never factually checked that. But let's see if 5 over 30, let's do the enlargement. If 36 over 5, does 36 over 5 equal the same thing as 78 over 9? And remember, those are the parts that you would compare in that way. Now, 36 over 5 cannot be reduced. 78 over 9 can be reduced, but not to what you want. 36 over 5 is over here. And if you divide these by 3, you get 26. Is that right? 26 over 3? Not the same. I just went straight reduction only. Now, 26 over 3 is just a hair under 9. 36 over 5, that's not even close. In fact, it doesn't even look close. 36 is less than half of 78. And 5 is more than half of 9. No, this was never going to be close. No. The rectangles aren't similar. Wait, the surfaces are not similar. The surfaces are not similar. I probably should have typed this. Because corresponding parts are not proportional. Corresponding side lengths. are not proportional. Sorry about that. Probably should have typed that. It said, if so, find the scale factor of the tennis court to the table. And there isn't one because it's not a similarity thing. Okay, number 37 and 38. In math, in 37 38, the two polygons are similar. Find the values of x and y. So on number 37, you have to find the parts that once again correspond. This corresponds to this. And you're going to have to make your best look at what other parts are supposed to correspond. They say these are similar here, but because there aren't enough lengths to show everything else off the right way, we're going to have to go off and say that those are similar. That means that the y part here corresponds with the 27 part here. It doesn't mean the y equals 27. That means that whatever y divided by 27 is, 18 divided by 24 is the same thing. So we can work it off that way. Same with x minus 6 and 39 being in the same breath as well. Let's start with the y though. Let's go y over 27 is the same thing from the right triangle to the left triangle is the same thing as 18 over 24. Okay, that's my setup there. Now that's also 3/4. So y over 27 equals 3/4. This isn't going to be a clean number. 4y equals 81, and y equals 81 over 4, 20.25. So there's y's value. X has x minus 6 is to 39 as, hey, 3/4, right? We saw the same thing before. And x minus 6 is in the smaller triangle, 39 is in the bigger one, so we'll do the same thing here. But when we cross multiply this time, once again, the 4 multiplies not just with x, but with all of x minus 6. And 39 times 3, 78, 107. Also not going to be a clean answer here. So 4x minus 24 equals 107, or 4x equals 131, or x equals 30. I don't want to get this one wrong. 32.75, 131. What is something's in my calculator's way? 131 divided by 4, 32.75. Okay, I hope I wrote all the numbers right, because sometimes whenever I have a decimal, it's like, well, I think they would have wanted us to have good numbers, but maybe they didn't as well. You never know, especially since this thing is a mathematical connections thing. It might be a little bit different there. Let's just be sure that all the numbers were right, because something seems like off in my head. Okay, I got what's off my head. This isn't 107. This is 117. 117. So that's going to change some stuff here. What was this number? What did I write here? Oh, 141 now. Now let's use the calculator. 141 divided by 4. 35.25. Okay, let's go off that. 35.25. Okay, let's keep moving forward. Number 38. More of the same, different kind of look. Now, take a look at what you see here. I think we have enough indicators to show what parts are similar or what parts correspond and what we do. This looks like it's kind of rotated upside down. So this 116 goes with this 116, right angle with right angle, and then where the 61 is here, this clearly looks like the 61 there, so that's, another one. So if I wanted to find y would correspond with this missing guy right here, or the y minus 73, I should say. So it'd be nice if we found out what this one was as well, just by knowing what we have of quadrilaterals. And I know I'm doing y before x once more here, but let's find out the missing angle on that one guy there. 61 plus 116 plus 90 plus this unknown, I'll call it A for angle, equals 360 degrees, the interior angle sum of a quadrilateral. 61 plus 90 is 151 plus 116 is 277. 116. 267? I really should be using a calculator. plus A equals 360. Let's just see what the answer should be a little more than 90, I think. So A equals, yeah, that's 93. Just because it looks more than 90, and normally they do that to scale. So this is 93, and that's what y minus 73 is equal to. Y minus 73 equals 93. Add 73 to both sides. Y itself is going to be 166. Now, x will correspond with the 5. I know this is not in the right orientation, but x corresponds with 5, like 6 corresponds with 4. So that's kind of like my setup there. Those are corresponding parts. And again, angles are congruent, but side lengths are proportional. So x over, oh, I lost my thing that I was writing with. X over 5 equals 6 over 4. It's kind of my setup for this guy. X over 5 is 3 halves. Let's reduce that. And multiply by 5, you get x is 15 over 2, or 7.5. So 166 for y, 7.5 for x. Okay, let's go to numbers 39 to 42, and let's attend to precision. The figures are similar, and we got to find the missing corresponding side length. So on number 39, we have figure A with a perimeter of 72 meters, and one of the side lengths is 18. Figure B is a perimeter of 120 meters. We got to find the side length that corresponds in figure A with figure B, knowing the perimeters. So the perimeter ratio comparing A to B or B to A, I don't care which. Let's do figure A is a perimeter of 72. Figure B is a perimeter of 120. 72 over 120, I think that's kind of a very clean, 20 divided by 24, right? I think it's 3/5. 3/5. So 3 to 5 for figure A to figure B, right? That's our setup. Well, from figure B to figure A, I should say. But here's A to B, like that, 3 to 5. And in side length A, the smaller one, we know that one of the side lengths is 18 meters. And in figure B, we don't know that following corresponding side length like this. So this is where we do the cross multiply and divide self. So the side length that corresponds with figure A's 18 meters is this 30 meter length that we have in figure B. Number 40. Figure A is a perimeter of 24, figure B is a perimeter of 36, and one of the side lengths is 12 inches. So now this time we know something out of figure B. Let's figure out something out of figure A. But if we do the ratio of perimeters from A to B, we'll have 24 over 36, which reduces to 2/3. So let's take that 2/3 and do a proportion comparison by figuring out this unknown figure A's length. That's going to be in the smaller figure. And B has a length there of 12 when we do this ultimate comparison. So if I multiply by 12, 2/3 of 12 is 8. So x is going to equal 8 inches in this case, in this comparison. Number 41. Figure A has an area. So now we're in area. Area 48 square feet. Ratio of areas is, so we have 48 square feet for A. Figure B is an area of 75 square feet. And that reduces, they divide by 3, 16 over 25. I think that's the smallest they reduced to 16 over 25. Now, that is the ratio of areas. The scale factor, the ratio of corresponding sides, remember, area ratio is the square. Here, let me write it this way. If I square a scale factor, I get the area ratio. So K squared is 16 over 25. So K, square root of both sides, is 4/5. So the similarity ratio that we work off is 4/5 to do this set. If I go 4 to 5 for figure A to B, small to large, one of the side lengths in A is 6. This corresponding side unknown is B, of B is x. Multiply, cross multiply, 4x equals 30. Divide there, I get x equals, I think that's 7.5. And this is in, they said square feet for these ones here, so this length is feet when we just talk about the lengths for comparison. Number 42, Figure A has an area of 18 square feet. We're going to do area one more time with the area ratio stuff. And if I lost you the first time, let's see if it will make sense this time. 18 square feet, and B is 14. This time B is the smaller one. So with that comparison, we can divide those both by 2, and we get 9/7. This is once again the area ratio. Okay, this one will be interesting because this is 9's a perfect square, but 7's not. So for figure... Oh, I'm sorry. This is why. Figure B's was not 14 for the area. That was the side length. So this is 98 here. Okay, divide those by 2. That's 9/49. Much better even for me. I was saying, uh-oh, there's that. So K is going to be the square root of the 9/49, which is 3/7. This is the scale factor ratio. This is where we compare side lengths and things like that. And that's why we need this one, because areas are squares of these things here. So 3 is to 7, A is to B, as A, the unknown for this length, is to B's 14-foot length here. And multiply by 14, 3/7 of 14 is 6 feet. There. Okay, numbers 43 to 48. I'm kind of excited whenever I see those, like a bundle of them, because I hope that there's small problems within and not a big set. Tell whether the polygons are always, sometimes, or never similar. So I'll kind of write sentences for these ones here. Two isosceles triangles. They don't say explain why, by the way. So, are sometimes similar. Look, the basis of this is that they could be similar, as long as they have the same number of degrees for each angle. And two of them will be the same regardless. But you don't have to have all the same angle measured degrees within two different triangles for isosceles triangles. It's just not a requirement. So if it doesn't ask me to explain, I'm not going to write it out, but that's my explanation. Number 44. Two isosceles trapezoids. Same thing. Two isosceles trapezoids are sometimes similar. I mean, the idea of saying sometimes, I wouldn't say when in doubt, guess sometimes. I would say that only guess sometimes if you can consider a case where it is true and where it's not true. And it's just very true that you can have two isosceles triangles and just want a bigger version of another and a bigger trapezoid version of another, but it's not required that they have to be that way. Number 45, two rhombuses. It's the same thing. It's still a sometimes. Two rhombuses are sometimes similar. And if you're not understanding without me making the visual, just go ahead and draw two. All the rhombuses need are congruent angles together and different side lengths, but not the rhombus, not within a single rhombus. 4, 4, and 6, 6, 6, 6, 6, 6, and just have the angles be the same. And then you have two that are similar. But then you could also just change the angles, and then they're not. Now, squares are a different story. You can't change a square's angles, and their side lengths are all congruent within each other in that set. So 46, two squares are always similar. There's no way that you can't make squares not similar to each other. Now, they can have a 1-to-1 similarity ratio. So as far as a trick question, are congruent figures similar? Yes. They're also congruent, and it's preferred that you probably say that. But they do have similarity, so you're fine there. Two regular polygons. Depends on what the polygon is, right? If it was the same polygon. So I'm going to say this. Two regular polygons are always similar if the same type of polygon is being used. Same type of polygon is compared. So like two regular octagons, like two stop signs, a small one and a big one. However, if they are different polygons types, then they wouldn't be similar. They would never be similar. They would just be different shapes. So I don't know which one they were going for. They didn't say of the same type, so I'm not sure if we were supposed to assume that. And then number 48, a right triangle and an equilateral triangle. I'm guessing that other one was supposed to be always, just based on what we saw. A right triangle, see, any equilateral triangle will be similar to another equilateral triangle. Not all right triangles will necessarily be. A right triangle is never similar to an equilateral triangle. Now, why? Because equilateral triangles always have all 60-degree angles. And a right triangle has at least one 90-degree angle. So if they have one set of non-congruent angles, then they're never going to be similar. Number 49, making an argument. Your sister claims that when the sides of two rectangles are proportional, 49, when the sides of two rectangles are proportional, the two rectangles must be similar. Is she correct? Explain her reasoning. Oh, okay, I got it. I thought she said just two different sets of sides. I was going to say, well, they could be opposite sides. The side lengths of two rectangles are proportional. The rectangles must be similar. Explain. Is she correct? Yeah, I think yes. So because the angles can't change. So your sister is correct because the angles can't change from being right angles. Therefore, if all sides are proportional, if all sets of sides of two rectangles are proportional, then those rectangles are similar. Okay. Yeah, go sis. All right, number 50. How do you see it? You shine a flashlight directly on an object to project its image onto a parallel screen. Will the object and image be similar? Explain your reasoning. You know, this is something that that's freaky. I thought this was a piece of paper that was going to be shined on something else. Flashlight directly on an object for that's scary. As long as the flashlight lens thing isn't curved or whatever, I guess it has to be a little bit. They're asking you to basically say yes. So 50, yes. I mean, just the idea of it. I did something similar, not with a bug, but I talked about a similar thing. If you shined, I talked about this with dilation, because like the flashlight can be like the center, and the light's coming out from the center. So yes. Why? Explain your reasoning. Because if parallel, then you create proportional corresponding side lengths. I don't know if it was skewed, right? If you shined it against something that's kind of at an angle, you get a bit of a skew of things. Some parts might be bigger because they're farther out than other parts that are in proportion with each other. Okay, 6 more problems, but this might be where it gets deep. Number 51. During a total eclipse of the sun, the moon is directly in line with the sun, and that's an eclipse, and blocks the sun's rays. The distance dA between, where's A? Here it is. Between Earth and the sun is 93 million miles. That's a lot of miles. Space is weird. It's hard to think about. The distance DE between Earth and the moon is 24,000 miles, to 240,000 miles. And the radius AB of the sun is 432,500 miles. Use the diagram and the given measurements to estimate the radius of the moon. So here we have triangle similarity once again, because we know we have, it's a radius with the center on this other thing here, just the way that it's provided on the total eclipse. These are right angles here. Because these are parallel to each other, alternate interior angles are congruent. Even if we didn't listen, maybe they're not right angles, but alternate interior angles are congruent anyway, or corresponding angles are congruent anyway. Things that we'll learn, and this is the same angle shared at this part here. A lot of reasons to show these are actually similar. If they're similar, these two parts correspond, AB with EC. So I'll even write it as an actual thing to begin with. AB over EC is in correspondence with the entire distance from Earth to Sun, AD, over the distance from Earth to Moon, Moon to Earth, which is ED. So these will have a proportionality together. There's only one that I don't know, and it's EC. I know AB as 432,500 miles. I don't know the length of EC, the moon's core, the radius of the moon. And this is equal to AD, which is 93 million, divided by distance between moon and the Earth is 240,000. So this clearly isn't drawn to scale in that way. I don't know what can reduce or not. Well, I can kind of, these can reduce here. So that over 24, I'll leave it as that as I work some of the cross multiplication stuff. So let's do 24 times 432,500. Honestly, I'm going to do this all on my calculator. Well, I have to write this out because then you know what I'm calculating here. 9,300 times EC is 1038000, and then divide both sides by 9,300. And you can look up this stuff online. It'll probably be close to it. They said approximately estimate the radius of the moon. EC is about, that's not the similar statement, that's just about equal to 1116, because they're decimals. It kind of goes forever. Let's just write 1116. Not truly forever, but 1116 miles. It's weird to think. It's weird to think of things with mile. It's just so big. All right. Number 52, proving a theorem. Prove the perimeters of similar polygons theorem for similar rectangles. Include a diagram in your proof. I mean, am I doing the whole triangle congruence proof thing? I'm trying to think of what they want us to do. I guess not a two column proof, right? It's not like CPCGC. So let me think about this. 52. So they didn't say indirect proof, right? They said something else. Okay, they said use a diagram, but you have to draw two different rectangles, right? Or did they say rectangles? What did they say? They said similar rectangles, yes. So let's do a rectangle here and a rectangle here, make one look like a bigger version of the other. We'll call this ABCD. We'll call this EFGH. They are rectangles, so we will know right angles here and then just parts that would correspond, right? So, hold on, let's see what they said. Prove the perimeters of similar polygons theorem for similar rectangles. Well, what they've been doing a lot of, and it seems to make sense for rectangle stuff. Let's say that we had some length here, just because it goes left and right, it's called X, and then up and down is called Y. And then if I wanted to find the perimeter of this guy here, this would be 2x plus 2y, both x's and both y's. Now, if we're multiplying by some scale factor, we generally call that k. This would be k times x and k times y. We even saw the same thing in like the first set. So the perimeter here is going to be 2kx's plus 2ky's, like that. The perimeter of the small, perimeter of the big. Now, they're saying that show that this is the same as the other thing. If I did a scale factor and divided, let's put this on top, which is the bigger one, 2kx plus 2ky, and divided it by 2x plus 2y, I need to show that that's equal to the same, well, that it's equal to k. I need to show that it's equal to k. So, because that's what k times x over x is and k times y over y is. So, does it equal k? Actually, let me not write it as k. Let me just write it as ratio. Let me write it as perimeter ratio. Ratio of perimeters. I can factor here a k. I can factor a 2, but that's not going to help. Of 2x plus 2y here. And I have 2x plus 2y. And those can cancel, if you will. It's one whole quantity, and that equals k. So r sub p equals k. And that just seems to match up, I suppose. I'm not sure if that kind of works everything out that I wanted to say, but that feels like it gets me the same k as what I get when I multiply by the set, and that would apply. And it wouldn't apply for areas, for example. So that is what I'm seeing there when I got that. So include a diagram, I got it. All right, number 53, prove that areas of similar polygons for similar rectangles. Include a diagram in your proof. I want to kind of just do the same thing. let's work that out and see if it does work in the same process that I wanted to. It's nice to have little proofs like these along the way, but I did it with TVs, fitting TVs. Oh boy. Okay, so here, let's consider the ratio of areas. Now, what we know is that we can take this k times x, multiply it with k times y, divide it by this x times y. Oh no, it's telling me I gotta reset and change my password for my school thing pretty soon. It's like in a few days. K times k is k squared, so k squared times x times y over x times y. And xy over xy, boom, is 1, and you're left with just k squared. So it's still showing the area ratio. I haven't really done these proofs like this before, but it makes sense to do that. And you get k squared out of it from the area ratio that we have there. These were rectangles. That's why I did x times y and kx times ky, because the area of a rectangle is base times height, length times width. And that's what I was doing for those ones. I think obviously I could do a whole paragraph proof, but I think that kind of just makes sense with this stuff here. Ooh, those get confusing. Let's see. Number 54, thought-provoking. Okay, the postulates and theorems you have learned represent Euclidean geometry. In spherical, there's one problem so far that I recall. There's one problem so far out of this entire book that I didn't do, and I never went back to try it. I could probably do it, but I don't know. I just looked back at, and it was a Euclidean geometry question. I remember 2 Euclidean geometry questions so far in the entire book. This is the 3rd I know, but that second one, I said, guys, I don't know. It's the last question. I'll just stop. So I just said I didn't know. Let's see if we know this one. In spherical geometry, all points are points on the surface of a sphere. A line is a circle on a sphere whose diameter, this is so hard for me to understand what they say, whose diameter is equal to the diameter of the sphere. A plane is the surface of a sphere. In spherical geometry, is it possible that 2 triangles are similar but not congruent? Explain your reasoning. I don't know if I'm going to get this one right. I have so much trouble. I know what they're saying with regard to, and I think that's part of the other problem. Even if I did know how to answer it, I don't know if I could answer it to you guys, because just the idea of a drawing of a sphere doesn't really work here perfectly. But, you know, it's just like imagine that this is around this thing here, like there's the back and then the other's the front. And then this could be considered the line because this could be the diameter here. And then you have an entire plane. But from here, they talk about things that could it be, did they say congruent but not similar, or similar not congruent? Similar but not congruent. I don't really know how this thing works. It's just the problem. It's one of the sets where I'm like, guys, I'm not really sure. But the problem here with being similar, the problem in the circle with having this thing is, once you have, I think on this thing, once you have a set triangle, it has very specific angles, and those angles will remain congruent with no matter what kind of triangle that you make on a spherical one. I don't know how to explain this one, but I think that answer is no. Is it possible 2 triangles are similar but not congruent? No, because, and I don't know if I'm saying this right, no drawing will be able to help me explain this to you guys, because a unique set of 3 angles in a sphere must be congruent to the other ones, to any other ones of that unique angle set. I just believe that with that specific sphere, we would only be able to get that very unique angle set to work out within one that's congruent, just because of how the size things work. I can't have this angle be this measure, and this measure without being that size. Once I grow the size of the thing, it's changing my angles on my object. I don't know how to explain it beyond that, because spherical geometry can just be terrible. I don't really know if that works. Anyway, that's what I got. Okay, number 55, 2 more. In the diagram, PQRS is a square. Oh, I know where they're going with this. PQRS is a square, and PLMS, this guy here, is similar to LMRQ, this guy here. So you have to look at where things correspond, P with L, things like that. This value is called the golden ratio. Golden rectangles have their length and width in this ratio. Show that the similar rectangles in the diagram are golden rectangles. Okay, you probably don't know what the golden ratio is, but this, I mean, they just explained it, but you probably might not have understood what was said. Here's what was said. In a rectangle, there's a very specific rectangle, and I probably didn't draw it perfectly enough where they did. There's a very specific rectangle with a ratio, like it's not 2 to 1, it's like 1.7, I forget what the number is. But this to this, there's a very specific ratio that I could, when I draw another line down here to make a square, the new rectangle also is in the form of a golden ratio. And then if I made another rectangle where this is a square, this one's also in the golden ratio. And then this guy, when a square is made, this guy's in the golden ratio, etc. And it keeps going. You can work inward, and it keeps just kind of working off that, which is really cool. Now, you can come up with that ratio value using quadratics. Using quadratics, you can do that. So we'll see what they want us to do here specifically. But in this set, I do have, and this is not a perfect scale drawing, but I do have a length here of 1 and an entire length here of x, where I have that P, Q, L, M, R, and S. And again, certain parts correspond because the rectangle goes vertical, or the big rectangle is horizontal, and this one's vertical. So you just got to know which ones correspond. Now, what do they want? Show that the similar rectangles in the diagram are golden rectangles. Well, here's the thing. If this is x and this is 1, then this thing here is x minus 1. This thing here is x minus 1. You take away 1 from that x, and that's what you get. So x, now here's where you got to be careful. X is from S to M. What? Oh, sorry. And this, if this is 1, then so is this one right here. And I think that that's really what you need. This S to M is corresponding to the Q to R for the other rectangle. In fact, let's do this. Let's draw these both out as two different rectangles now, so that face the same direction. So let's do it so it looks like in the big guy, S to M, I have a length of X. And in this guy here, Q to R, I have a length of 1. This is Q and R, where this is S and M. And also in S and M, if these are 1s right here, this is 1, this is 1. And this is also going to be 1 right here from L to M. So that's a 1. L, and here's P. And then for Q and R right here, I have L and M right there. And this is 1. This guy here is X minus 1. So what we can see are the parts that correspond, let me make this a 1, are the parts that correspond in each of these things, where I could say x over 1 equals 1 over x minus 1, x over 1 equals 1 over x minus 1. And I can cross multiply. Oh, I think this is going to give me that golden ratio thing. Show the similar rectangles are golden rectangles. I don't know if they're asking me to find the golden ratio itself, but here's a setup that can get us there. Cross multiply, we get x squared minus x equals 1, and then x squared minus x minus 1 equals 0. You could solve that algebraically. I don't know if that's they wanted us numbers, but when we get this answer, we can show, yeah, maybe that's what we do. Maybe we actually solve for this thing algebraically, because I'd be ready for that. But when we do solve it algebraically, then we can show that this works out and satisfies that proportion. So I would solve this probably with the quadratic formula, where I would say x equals negative b plus or minus, I'm not going to teach you how to do this again, plus or minus the square root of b squared minus 4ac, all divided by 2a. So x equals 1 plus or minus the square root of, that's 1 minus negative 4, or 5. 1 plus over 2. So here are the two different values of x that we can use. Now, you'd have to actually go to the calculator and plug that in and see that this gets you at here and here. You do get the same number. Remember, there are two different answers. There's 1 plus root 5 over 2 and 1 minus root 5 over 2. Let me give you their approximations and show you that you can try that with that proportion and, say that it works. This didn't compute. 1 plus the square root of 5, and that divided by 2. So I got 1.6, that was it, 1.618 for that value of x. Now, there's a 1 minus root 5 over 2, but I don't think you can use it because that would give you a negative number. So we're going to have to just use the plus for that side of the answer there. 1.618 is also about the same as 1 over 1.618 minus 1. Yeah. Okay. Okay, so yeah, I'll just say that it works out. This satisfies the proportion. Okay, and the last problem here is number 56. Let's check it out. Mathematical connections. The equations, 56. The equations of the lines shown are y equals 4/3 x plus 4 and y equals 4/3 x minus 8. Show that triangle AOB is similar to triangle COD. Okay, so I'm not going to like write out a 2-column proof kind of thing, because here's the thing. You don't know about triangle similarity yet as a whole as far as which things you can use to conclude. But for us, I think it's enough for us to be able to say what I want to say here, that these, for the parts that correspond. But I'll just show you as many parts that correspond as possible. Okay, so first of all, you're going to have right angles. You're going to have a right angle here and a right angle here. Now, even if you didn't know they're right angles, you should, because they're x and y axes. They're also vertical angles, which are congruent. Now, with the 4/3 for these, that means these lines are parallel. And here you have alternate interior angles that are congruent here and here. And then alternate interior angles that are congruent here and here. So all of them have corresponding sets of angles that are congruent, which is actually by far enough to show that the triangles are similar. Now, you also have y equals 4/3 x plus 4, and that plus 4 means that the 4 is the y-intercept, that length is 4. This is y equals 4/3 x minus 8, and that means that this length down here, negative 8, is 8 right there. So this has a 2-to-1 ratio. 8 to 4 is a 2-to-1 ratio for the big triangle to the small triangle. But also that means that you have this kind of rise of 4 and run of 3 right here to get to that point. And this thing has to rise 8, therefore to run 6 to get over here, because that's how the slopes work. And using Pythagorean theorem, I could then find out 4 squared plus 3 squared is actually 5 squared, and 8 squared plus 6 squared is 10 squared here. So I'd have enough. Oh, here's where the 3 would go, by the way. So every part of this triangle I can establish here as either congruent or proportional in this way. So here we go. I'm going to show every single part. The triangles shown are similar. The inner angles, the inner right angles, are congruent vertical angles. And by alternate interior angle theorem, the other two sets of angles are also congruent because the lines are parallel. Now, that's the first part. The second part are all the side length things that we have as well. Using slopes and Pythagorean theorem, all side lengths, I use Pythagorean theorem on the two sets of the hypotenuses, all side lengths can be measured, and then I can compare those things here. I can divide 10 by 5, 8 by 4, and 6 by 3. 10 over 5 equals 8 over 4 equals 6 over 3, which all equal 2. And that would be the scale factor. There is a scale factor of 2 in the enlargement. In an enlargement, there is a scale factor of 2, as the side lengths are proportional. Because all angle measures are congruent, all angles are congruent, and all side lengths are proportional, triangle, I have a triangle symbol here somewhere. Give me 1 second. I'm done after this. Triangle AOB is similar, and it's the parts that correspond to triangle COD. Okay, and that'll be it. So that's where I went with that one, and I think that that one is sufficient. All right, guys. I'll leave it down there for a bit. But all right, guys, and that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. And this one's pretty good because there weren't a lot of graphs, there weren't a lot of proofs and things like that. The last things don't really count in the same way. A lot, I wouldn't call it drill and kill, but a lot of them were more examples where you got to compute numbers. And that's good for our bases just talked through. Let me know if you have questions on things, the areas and stuff. I hope I calculated all the numbers right when I did or didn't use the calculator, or at least I hope I corrected the ones that I needed to. So thank you guys. Everything that's going to be coming afterward, I think I forget in the sections, but they're really going to start probably touching on the triangles in the next couple sections now that we've talked about similar polygons. All right, guys, take care. I'll see you in the next one.